Welcome to Lyons Township High School Physics AP, and today we have an example. This is for those of you taking Physics C here at Lyons Township. This will be your last video example of the year. Don't clap too loud. All right, so here's the deal. We have what we call mutual inductance. Let me give you an example or two of how that works. Also, you're going to want to copy down this diagram. We have two solenoids right next to each other, like so. And we're going to have them eventually have different radii. So imagine you have, let's say an electric toothbrush, or you have one of those cell phone chargers where you just throw the cell phone down onto a pad and it charges, okay? How does that work, all right? Well, it's really simple. What you have is you have two coils of wire, okay? They're usually not going to be the exact same size, so maybe you have something like this, one coil here, one coil there, like that, okay? And what happens is current flows in the one coil that's plugged into the wall, let's say. That's an AC current, so the current is changing constantly, therefore the magnetic field generated by the solenoid is changing with time as a sine function. Your item, being maybe your electric toothbrush or maybe your cell phone, has a coil of wire in it as well. When this current changes and changes the magnetic field within this solenoid, that tries to change the magnetic field within this solenoid. This conductor says, hey man, I don't like that. I'm going to make a current that opposes that change in flux. That is Lenz's law. Now, having said that, in order to make that current, a voltage is generated in this solenoid. And so basically what we're doing is we're seeing how good is this system at creating a voltage over here, and that's how you charge your cell phone or charge your electric toothbrush, okay? Without, by the way, these two things touching it all. And again, you got a magnetic field that changes. That's the key here, guys. It changes. Therefore, this guy says, I don't like change. I'm going to make a field pointing the other way to oppose that, let's say, increasing field at that moment. And therefore, a current is generated over here. That current is generated by an EMF, aka a voltage. So what we're going to calculate is we're going to calculate what we call the mutual inductance of the system. How good is it at making a voltage over here? Okay. Now, I will give you a couple of reminders first. So first of all, you had the two solenoids. We're going to say they have different radii, so something like this, or even something more drastic like this maybe, okay? And we are going to give these some values. Now, we're not going to use numbers, but let's say this solenoid had a length L1, and it had a number of turns N1. And then similarly, that's L2, got a number of turns N2, okay? And over here, you have an input current I, and that varies with time. If it's like, you're plugged into the power company, that's a sine curve. It's cycling at 60 cycles per second, 60 hertz, okay? Two equations that we've already talked about is what is inductance. So inductance is N flux, magnetic flux, over I. Okay, so that's how you calculate the inductance of an inductor. And we've done several examples of that in class. The second part of this is how do you find EMF? Well, it's negative L di dt. Okay, so we're gonna do something very similar here. We're gonna have an equation that kind of tells you how good these two are with each other. It's not going to be L exactly, but it's very similar. And then we're going to plug that in here to get the EMF over there. Okay, so we call mutual inductance. We call the variable, instead of using an L, we use an M. So a capital M. Okay. And it's defined similar to this, okay? It's the number of turns in this coil, so that's N2, times the flux that passes. So imagine, and I'll draw this kind of light, we'll use some hot pink here. The flux that passes from 1 into 2, so I'll kind of draw it that way, the magnetic flux that passes from 1 into 2, okay, over the current of 1. So how good is this current at generating a voltage over here, in essence, okay? All right, now we have some equations here. we'll say that again, that's M, and we'll label it 1 to 2. Okay, that's the way to think of it. So that's going to be N2, okay, times the flux that goes from here to here. Okay, well, how do we calculate that? Well, flux is B times A. Now I'm going to use the simplified version of it. We're not going to do the integral and all that. We're going to assume that the B is constant throughout this region, and then we have some area, okay? And then times or over I1, okay? Hey, it's MBA. All right. Now, for B, that's the magnetic field made by 1. So that's B sub 1. So the magnetic field created by a solenoid is mu naught, the number of turns in the solenoid over the length of the solenoid times I1. So that's B1. Now, by the way, you'll note, and we've discussed this in class, the current should go away. How good this system is at making a voltage here isn't going to depend on the current flowing, okay? So we're going to plug that in for B1. I'll do that down here. So the mutual inductance of 1 to 2 is N2 times B, which is mu naught N1 over L1 times I1, okay, over I1. Oh, and then we have our area there. Okay, now notice I haven't put an A1 or A2 there yet. That's coming up next. As I just mentioned, you'll notice that I1 drops out, of course. Okay, now which area do we need, guys? All right, well that's a little tricky. Okay, so I'm gonna use an example where the two areas are vastly different to kind of illustrate this. If I have this, here's my input, here's my output, my toothbrush, okay? First of all, I hope you would agree that all the flux, or virtually all the flux coming out of the gold solenoid will go through our hoop, right? So how do I calculate all the flux coming out of here? Well, that's just B1 times A1, okay? Now, that field, that flux, it may spread out as it enters here, but so in other words, B may decrease, but A is increasing, and the total is still going to be this B times this A. However many field lines jump out of here, they're going to go through here if I have them close together, okay? So in that case, you would use this area, okay? You wouldn't care about this area because, like, you know, for instance, this flux coming out of here, it ain't even going to cover this entire area. It's only going to cover a small area if I hold this close, okay? But what if I flip it around? What if this is the input and here's the output, okay? So I can calculate the field coming out of here. We did that right there, okay? If I take that B times that A, does all of that flux, do all of those field lines go into here? No way. Most of them pass this way, over and under, and, you know, on the side of it. Only a few of these field lines will enter there. Now, assuming that this field coming out of our input is relatively constant, okay, or assuming this is relatively close to it, okay, then you'll take this B for flux, this B times the area it's entering, which is this little guy right here. So hopefully you noticed in either case, which area do you use? What's the general idea? You use the smaller area, okay? So when we put A here, okay, it's whichever one is smaller. Okay, so for our example, let's just say that R1 is less than R2, just for our example. Okay, so we have this example, okay, where here's our input and there's our output. All right, so using that, okay, for area here, in this case, is going to be pi R1 squared, okay? So the mutual inductance of 1 going into 2 is N2 times mu naught N1 over L1 times the area of whatever the smaller one is, which is pi R1 squared. And that's pretty much your answer. So the mutual inductance of 1 to 2 is, now I'll kind of rearrange this. We got mu naught, we got a pi, we got an N1, N2. okay? We have an R1 squared. But in general, and I'll make a note of that, that's always the smaller of the two radii over L1, okay? That's our answer. That's the mutual inductance between 1 and 2. Now notice, another thing to notice, just for helping you remember stuff, that equation versus the equation of inductance for a simple inductor. For a simple inductor, for a single solenoid, its inductance is just N squared. And everything else is the same, okay? So here you got two solenoids, so you just say N1 times N2. Otherwise, the equation looks almost exactly the same. Now, having said that, how would you find EMF now, okay? Well, you would do EMF in 2, okay, is negative M di1 dt. So you would, theoretically, you'd have all these values in the problem, N1, N2, R, L, L1, etc. So you'd have this value here, and they would need to give you the current as a function of time. And if it's like plugged into a wall socket, it would be a sine function, so you'd get a cosine function there, or vice versa, and that would be your answer. That would be EMF as a function of time, which of course would vary as a sine or cosine function. Again, the negative sign is all to do with Lenz's law. You don't have to do it in the calculation. It's just get the magnitude of this. So basically, that's an example of, like, you know, how does something charge something else without making metallic or conducting contact with it? Well, here's one way to do it, okay? And we call that mutual inductance. How does the changing current in one solenoid make a current flow, and how good does that do that in the other solenoid? So I hope that was helpful. And again, if you're with LT here, this is your last video example. So I hope it was helpful and you enjoyed it. Thank you very much.